doing the next section in chapter 2, and this next section is going to kind of take us a little bit of a different turn. So we've been spending a lot of time on polynomials, and we are going to move to what are called rational functions. And they use polynomials, but in a little bit different way, right? They use them in terms of a fraction. So we are going to start off by looking at lots of characteristics of these rational functions, specifically with respect to their graph, because the function, equation, and graph are all so connected, right? The equation tells us stuff about the graph tells us stuff about equation. So how are the graph's characteristics calculated and used? So first of all, a rational function, r of x, is defined as f of x over g of x, and f and g are both polynomials. The parent function for a rational function is 1 over x. Super basic. 1 is a polynomial, it's just a constant, and x is a polynomial, it's just a linear polynomial. So that's kind of how we're working through this. So first of all, a quick example. 1 over x minus 2 plus 3. So that's a parent function. That uses the parent function of 1 over x. This minus 2 moves our graph right 2. And this plus 3 moves our graph up 3, based on what we talked about in 1.6. So if I draw a graph here, one, two, three, four, five. 1, 2, 3, 4, 5, 6, 7. Close enough. Whatever you end up with is great. This graph, if I was don't draw this. Just listen with me for a second, but don't actually draw this. If I was just drawing the graph, it would look something like this. Right? We talked about parent functions in 1.3. That would be the parent function. We need to take that graph and move it 1, 2 to the right and up 1, 2, 3. So to best do that, now you're actually going to write, we're going to start by drawing some asymptotes in. We have a vertical asymptote at x equals 2. X cannot actually equal 2 because that will cause a 0 in the denominator. Also, because this graph is shifted up 3, our horizontal asymptote is moved to y equals 3. Which means our function now sits like this. And I'm just sketching it. We can say lots of things about this function. One thing we can say is the limit as x approaches 2 from the right of this function is infinity. And the limit as x approaches 2 from the left of this function is negative infinity. The limit as x approaches negative infinity of this function is 3. Same thing over there, positive infinity. The limit as x approaches positive infinity of this function is also 3, because that's what our asymptote says. So that's a basic form of this function. Now, in order to do more with this, we are going to need to be able to talk about some of these asymptotes and whatnot. So the first thing we're going to talk about is horizontal asymptote. But I'm going to set up our notes here. So first, I'm going to talk about some graph characteristics. So the first characteristic of our graph, instead of calling it a horizontal asymptote, I'm going to change the name a little bit to end behavior asymptote. In your delta math, everything will be horizontal. but I'm just going to talk about it in general. To determine the end behavior asymptote, in other words, what's happening out at the infinities, we find it by checking the degree. Okay? One of three things will happen. If the degree of the numerator is less than the degree of the denominator. In other words, if the largest exponent in the numerator is smaller than the largest in the denominator, you have an end behavior asymptote of y equals 0. If they are equal, our asymptote comes from a fraction. We take the leading coefficient of the numerator and divide it by the leading coefficient of the denominator. If, let's see, we did less than, we did equal, so let's do greater than. If the numerator is greater than the denominator, we have to do some division, and we're not going to go down that rabbit hole. So for the most part, it's either going to be y equals 0 or y equals some fraction. So that's our end behavior asymptote. Again, delta math is going to live in the world of horizontal. If we're talking horizontal, we should talk vertical. Vertical asymptote. Vertical asymptote occurs at numbers, x values, that make the denominator equal 0. These numbers, they cannot also make the numerator equal 0. That's kind of a rule. So we're looking for where the denominator is 0. It's another important characteristic, our vertical asymptotes. X-intercepts. An x-intercept occurs at numbers that make, here it comes, this is why we had that wrinkle last time, that make the numerator equal 0. Our rule, they cannot also make the denominator equal 0. In other words, they have to be unique to the numerator. Y-intercept is the result when 0 is substituted for x. And then the final thing is called a hole. We've looked a little bit at holes when we did discontinuities. Holes occur when, remember those parentheses when I said that we couldn't be in the numerator and denominator both? This is why. A hole occurs when the same factor is in the numerator and denominator. Now, holy words. Let's go pick out some of our favorites. Vertical asymptotes happen in the denominator. Okay. X-intercepts happen in the numerator. Y-intercepts happen when 0 is substituted in for x. Holes occur when we have the same factor. And you know what? If I take it to the top, we check our degree. Now, you're going to do this in Delta Math, so I'm going to put together something that'll help you walk through that. But here are the basic notes for this particular section. You got this.